Welcome to my video course on railway safety and systems engineering. Today, we're looking at the immense responsibility of railway engineering. In this world, a single failure can be absolutely catastrophic. Just think about the sheer mass and incredible speed of a modern train. Trying to safely mitigate all that kinetic energy means safety isn't just a priority, it is literally the absolute foundation of the whole shebang. We're talking from the initial drawing board right through to the scrapyard. So, we're going to trace the chronological journey of this critical infrastructure, from birth to death. Our syllabus today covers concept and system design, development of safe systems, installation and rigorous testing, operation and system maintenance, and finally, decommissioning and safe disposal.
But before we step into the first phase, we really need to understand the RAMS framework: reliability, availability, maintainability, and safety. These are essentially the core engineering metrics we use to keep the railway dependable through every single phase of its life cycle. And the true engineering challenge here, as you'll see, is balancing really high availability with absolute safety, all without making the system completely unmaintainable.
Okay, let's dive into this. Phase 1. Concept and system design. Safety doesn't just happen. It's built in from the very beginning. Notice how this process flows. Long before any actual hardware is even conceptualized, engineers are out there proactively identifying hazards and evaluating their root causes. We then determine strict safety integrity requirements to create a complete, airtight safety requirement specification. It's all about mitigating those risks on paper first, right? Mapping out literally every conceivable edge case before a single line of code gets written.
And that brings us to a massive threshold: SIL 4, or Safety Integrity Level 4. Modern mainline interlockings absolutely must meet this exact standard. To put that into perspective, the mathematical likelihood of an unsafe failure in these systems is incredibly small. Achieving it often takes super complex hardware redundancy and totally diverse software programming. It is the absolute highest level of safety integrity possible for industrial control systems, which basically means the system is mathematically proven to fail safely.
Moving right along to Phase 2, development of safe systems.
Now, what's really interesting about this architecture is how the interlocking system acts as an impenetrable safety layer. It's basically a fortress. It receives requests from the control center, sure, but it will only actually send commands out to trackside objects, like the points and signals, if it is absolutely safe to do so. It's the ultimate gatekeeper of the railway. It is constantly checking and rechecking track conditions against these incredibly strict logic tables before granting any movement authority whatsoever.
During development, engineers use two totally contrasting strategies. First, we purposefully avoid faults during the design process. We do this by derating components and keeping the initial designs incredibly simple. But since absolute perfection just isn't possible in the real world, we also build in fault detection. By utilizing continuous in-service self-testing and defensive programming, the system can actually catch unavoidable issues and degrade gracefully. That ensures everyone stays safe even when individual components decide to fail.
Which brings us to Phase 3, installation and rigorous testing.
Testing isn't random. It follows a strict chronological hierarchy to guarantee absolutely nothing slips through the cracks. We start with Phase 1, unit testing of the individual software or hardware pieces. Then, we scale that up to integration and interface testing in Phases 2 and 3. Finally, we hit Phase 4, full test and commissioning. This rigorous sequence is a non-negotiable requirement to uncover any hidden faults or integration clashes before a single passenger ever boards a train. At the end of this massive gauntlet is final commissioning. The tester in charge actually signs the system into service, but only when they are unequivocally sure it works safely. Sometimes this even means running dedicated route-proving trains. They will literally send physical rolling stock through the sections just to stress test the digital assumptions, verify train detection, and make sure every little thing adheres strictly to safe railway principles in the real physical world. Let's move to and see how this builds into Phase 4, operation and system maintenance. We have to consider the human element in the control center. The operators there rely heavily on continuous system availability and perfectly accurate indications. Because here is the harsh operational reality. Poor system availability forces those operators to fall back on manual procedures. And since manual procedures lack the hard, fail-safe protections of the automated interlocking system, they are open to human error and are inherently far less safe. Maintaining uptime is just as vital as maintaining the safety logic itself.
But what actually disrupts this reliability? Well, the physical world is pretty hostile to electronics.
For instance, track circuits might incorrectly show a section as occupied when it's actually completely clear, simply due to flooded ballast or degrading track fixings. Environmental factors like electromagnetic interference, extreme vibration from passing trains, and wild temperature swings play a huge role. And interestingly, a major organizational cause of ongoing poor reliability is simply failing to deeply analyze and learn from past failures.
So to combat all those elements, we rely on 4 distinct maintenance strategies. Preventive maintenance is all about scheduled interventions, kind of like changing the oil in your car before the engine blows. Predictive uses remote condition monitoring to spot anomalies and fix things right before they break. Then we have reactive corrective repairs for when things inevitably do fail unexpectedly. And renewals, where we completely replace items before long-term wear becomes a real liability. The ultimate goal, keep the system highly available and minimize any dangerous disruptive work near the live tracks.
And finally, we reach the end of the line. Phase 5, decommissioning and safe disposal.
Decommissioning is a massive, highly regulated change. Environmental factors have to be managed meticulously. For example, legacy materials used in older systems, we're talking heavy cadmium batteries or outdated wiring, they require expensive, specialized disposal facilities today. You can't just unplug a machine and walk away. Retiring physical infrastructure safely without disrupting the ongoing operations right next to it requires absolute care and some serious logistical planning.
Which leaves us with a pretty provocative thought about managing that whole operational transition safely. Is removing an old, trusted system just as dangerous as introducing an unproven new one? It's a critical challenge engineers face during every single system upgrade, making sure trains continue to run securely while the environment changes entirely around them. Thanks, we can see you in next video.